Welcome to another webinar from the ADROIT6G project. Today, we will focus on the real-time holographic teaching proof of concept. Imagine a world where an expert appears as a full three-dimensional hologram in a remote classroom interacting with students as it physically present. A surgeon could guide a procedure live from another country, or a scientist could explain complex concepts while standing virtually in front of students. This is the vision of real-time holographic teaching, and in this webinar, we demonstrate how ADROIT6G makes it possible. This concept goes far beyond conventional video communication. Instead of observing a flat image on a screen, users experience a shared spatial environment where presence, depth, and interaction feel natural and intuitive. This result is not just improved communication, but a fundamentally different way of learning and collaborating. However, despite its potential, holographic teaching is not yet widely deployed. The reason lies in three major technical barriers: latency, bandwidth, and computational demand. Latency refers to the delay between an action and its perception. Even delays slightly above 100 milliseconds can disrupt interaction and break the illusion of shared presence. Bandwidth is another critical constraint. High-quality holograms require the transmission of extremely large volumes of data, often in the range of multiple gigabytes per second. Finally, computational requirements are substantial. Rendering a real-time three-dimensional holograph requires processing capabilities that can exceed those of high-end computer systems, especially when supporting multiple users simultaneously. Together, these constraints make holographic communication one of the most demanding applications for modern networks. In a current cloud-based approaches, the system follows a centralized processing model. Volumetric data is captured at the source and transmitted to distant cloud data centers where reconstruction and rendering takes place. The processed output is then streamed back to end users. While this model is suitable for many applications, it introduces critical limitations for holographic communication. The long transmission path increases latency, making real-time interaction difficult. Bandwidth demand accumulates in the network core, leading to congestion. And as the number of users grows, the system must replicate rendering processes, resulting in poor scalability. These limitations highlight the need for a fundamentally different approach. ADROIT6G addresses these challenges by rethinking how network and compute resources are distributed and managed. Instead of relying on centralized cloud infrastructure, processing is pushed closer to the users through edge computing. In this architecture, user equipment can act as a virtual base stations, contributing both networking and computational capabilities. At the same time, artificial intelligence is used to orchestrate resources dynamically, ensuring that compute, storage, and network capacity are allocated efficiently based on real-time demand. This combination of distributed edge intelligence and AI-driven orchestration enables a more scalable, responsive, and efficient system. We now move from concept to implementation, demonstrating the full end-to-end holographic teaching workflow enabled by the ADROIT6G architecture. The process begins with volumetric capture of the instructor. Instead of using a single camera, multiple RGB and depth sensors are positioned around the subject. These cameras simultaneously capture the instructor from different angles, generating a detailed three-dimensional representation known as point cloud. This point cloud consists of millions of data points that describe both the geometry and motion of the instructor in real time. The result is a dynamic and highly accurate digital representation that can be reconstructed into a holographic model. Before transmission, the captured data must be processed and optimized. The multiple input streams are synchronized and fused into a unified representation. Compression techniques are then applied to reduce data volume while preserving visual quality, enabling efficient real-time transmission over the network. This step is critical for balancing performance and resource utilization. The compressed volumetric data is transmitted over the network infrastructure. This stage places significant demands on bandwidth and latency as the system must sustain high data ranges while minimizing delay. ADROIT6G leverages advanced wireless technologies and optimized data paths to ensure this transmission remains efficient and reliable. Upon reaching the network edge, the data is processed by a distributed set of compute resources. These resources are not confined to a single server, but instead formed by multiple interconnected devices acting as a collaborative compute cluster. This cluster, referred to as a collaborative service provider, enables processing to occur closer to end users, significantly reducing latency and improving responsiveness. By distributing the workload, the system avoids bottlenecks and improves scalability. Within this distributed environment, the system reconstructs the three-dimensional holographic model from the incoming point cloud data. This involves combining spatial and temporal information to generate a coherent representation of the instructor. The workload is partitioned across multiple nodes, allowing parallel processing and faster execution. This distributed reconstruction is a key innovation that enables real-time performance. Following reconstruction, the system performs real-time rendering of the hologram. Rendering transforms the reconstructed model into visual frames that can be displayed on user devices. These frames are generated continuously, maintaining smooth motion and visual consistency. The use of distributed compute resources ensures that rendering can keep pace with real-time input. A critical requirement for immersive experiences is viewpoint-dependent view rendering. Each student may observe the hologram from a different position, requiring a unique visual perspective. The system generates multiple synchronized views tailored to each user's viewpoint, ensuring spatial accuracy and immersion. This capability distinguishes holographic communication from traditional video streaming. The render frames are then streamed to XR devices used by students. These devices display the hologram within the user's environment, creating the perception that the instructor is physically present. The combination of low latency and high visual fidelity ensures that the experience remains smooth and realistic. In addition to visual rendering, the system supports real-time interaction. Students can communicate with the instructor using audio, which is transmitted back through the network with minimal delay. This bidirectional communication enables a fully interactive learning environment, preserving the dynamics of traditional classroom. As more students join the session, the system dynamically scales its resources. Additional compute nodes can be integrated into the edge cluster, and workloads are redistributed accordingly. This allows the system to maintain consistent performance even as demand increases, supporting multi-user scenarios without degradation. Throughout the process, the system continuously monitors key performance indicators such as latency, throughput, and resource utilization. These metrics provide real-time feedback on a system performance and ensure that quality of experience targets are maintained. Artificial intelligence plays a central role in maintaining system efficiency. AI-driven orchestration dynamically adjusts resources allocation, routing decisions, and compute placement in response to changing conditions. This enables the system to adapt in real time, ensuring resilience and optimal performance. The results demonstrate that the system can achieve low latency, high reliability, and effective scalability. These outcomes validate the feasibility of real-time holographic teaching using distributed edge infrastructure. In conclusion, this proof of concept shows that holographic communication is no longer a distant vision. By combining distributed edge intelligence with AI-driven orchestration, ADROIT6G enables immersive, scalable, and real-time teaching experiences, paving the way for future 6G applications.